This video is about the implementation of the digital elliptic filter. The filter is highly selective with an order of 10 and a fall off of approximately -1700 dB per decade. The passband ripple is greater than -0.1 dB and the stopband ripple is less than -60 dB. First, I'd like to demonstrate the digital elliptic filter. Here is the sound of a chord of flutes. Here is the same sound filtered with a second order Butterworth low-pass filter that sweeps up in frequency. It is the same filter as a typical low-pass filter with no resonance. Here's the same sound again with a 10th order elliptic low-pass filter that sweeps up in frequency, the filter that this video is about. And you've just heard a near ideal low-pass filter sweeping up in frequency. For the prototype filter design, I use Scilab. All of the code is available online at GitHub through a link in the description. Let me run the Scilab script. This is Scilab, and it has run the script which opens a bode plot, the magnitude and phase of the frequency response. As you can see, the magnitude closely approximates an ideal transfer function. I'll expand the bode plot to get a closer look at the response. Here's -60 dB in magnitude. As you can see, the stopband ripple is below -60 dB. The passband ripple isn't visible at this scale. Let me zoom in to show you the passband ripple. And zoom in again. And there's the passband ripple. Here's -0.1 dB, and the passband ripple is greater than that. I'll open the Scilab script to show what I did with the pole zeros and gain. And here's the Scilab script. Here's the function that calls the analog low-pass filter design. As you can see, it has multiple arguments for output. Let's examine some of the outputs. Let's examine HS poles. These are the poles of the transfer function. There's 10 roots, 5 conjugate pairs. And here's the zeros. 10 roots, 5 conjugate pairs, and they're all imaginary. The smallest rational polynomial factor with real coefficients is a rational of 2 quadratic polynomials, or a biquad. The numerator is the product of 0 conjugate pair binomials, and the denominator is the product of pole conjugate pair binomials, as shown in the comments. To yield the coefficients for the biquad, we expand one of the products. S minus A times S minus conjugate A equals s squared minus a plus conjugate a times s plus a times conjugate a. That equals s squared minus 2 real a times s plus a times conjugate a. Since the zeros are purely imaginary for the elliptic filter, the coefficient for s is 0, and the final form for the stage is this. That can be further simplified to the coefficients that we're looking for. S squared plus c numerator 0 over s squared plus c denominator 1 times s plus c denominator 0. Further in the script, I open the elliptical coefficient file and test for errors. Then I write out the number of stages, the gain, declare a structure of coefficients, and then declare an array of coefficients. Then I iterate over the stages, calculating the coefficients, and then printing them out. And then finally, closing the declaration and closing the file. And here's the coefficient file. This is what the Scilab script printed out. This will be used to implement the filter with a LADSPA script, a LADSPA plugin. And that's all for the prototype filter and the biquad coefficients. Now it's time for digitizing the filter. Once the prototype filter has been determined, the conversion from the analog domain to the digital domain can be made. To compute the bilinear transform, I used the computer algebra system known as Maxima. I'll open the Maxima script. The analog biquad filter function is defined as a function of s. Calling this function will substitute the argument passed in for s. Then the bilinear transform substitution with frequency warping is defined. And finally, the bilinear transform substitution is passed to the analog transfer function to yield a digital transfer function in the Z domain. From there, the expressions for the coefficients can be inspected. To make the inspection easier, I wrote a Maxima function that prints out the coefficient expressions. It prints the coefficients in reverse because it is implicitly going from polynomials in terms of powers of z to polynomials in terms of powers of z to the minus 1 by multiplying the top and bottom by z to the minus n, where z is the order. I'll run the Maxima script. And here are the expressions for the coefficients. A0, A1, A2, B0, B1, and B2. These expressions can be used to implement the filter. With the coefficient expressions at hand, it was possible to implement the digital elliptic filter. To test the filter with a GUI, I wrote a LADSPA plugin. LADSPA stands for Linux Audio Developer's Simple Plugin API. In this case, it only requires one control, the frequency. I'll open the source file. I want to emphasize the BQ set function. This is where the expressions for the coefficients are used to initialize the coefficients for this stage. I'll run the Maxima script again to show the correspondence with the source code. Here are the expressions from the Maxima script. As you can see, the expressions are the same. Here's A0, A0, A1, A2, B0, B1, and B2. I'm not going to go into the source code in any more detail. You can go over the code if you want to. So there is the implementation of the digital elliptic filter. I hope you found that useful. Goodbye.